Hello and welcome to helpyourmath.com. In this video, we're going to look at finding zeros of a function, which also means we're going to determine values of x for which f of x is equal to 0. In this video, we are going to look at different types of functions, including linear functions, quadratic functions, and absolute value functions. So if you need to review certain techniques we use, like say for quadratics factoring, or for absolute values just solving an absolute value equation, links for videos for those will also be posted. Okay, so let's get started. What does f of x equals 0 mean? It means we're trying to identify the zeros of a function, which also means we're looking for the x-intercepts of a function, right? Because when we're talking about a function, we would say that the ordered pair would be x, f of x, and if f of x is equal to 0, then we would have x comma 0, which indicates that we're dealing with an x-intercept. So we're trying to identify the x-intercept or intercepts of the given function. There's various strategies for solving f of x equals 0. As I said, videos are available if you need to review quadratic, how to solve a quadratic, whether it's by factoring, quadratic formula, or completing the circle. And also videos for solving absolute value functions and videos for solving radical functions are all available should you need some review. Okay, so strategies, it really depends on the type of function you're given. If you're given a linear function, isolate the variable using inverse operations. If you're given a quadratic function, keep the equation set to 0 and see if it's factorable. If it is, factor away. If it's not, then you want to use completing the square or the quadratic formula, whatever you're comfortable with. If you're given an absolute value function, isolate the absolute value expression and set up the two cases. I say set up the two cases, I'm assuming that the absolute value expression is equal to something positive. If it's not, then you have to kind of see what to do. If it's equal to 0, then there's only one case. If it's equal to something negative, then there were no zeros to begin with. And if you have a radical function, isolate the radical, square both sides, check for extraneous solutions. In our first example, we're going to be given a linear function. We want to find all values for which f of x equals 0, given f of x equals 3x minus 8. So again, this is telling us we're going to replace f of x with 0. So this would be 0 equals 3x minus 8. Now it's linear, so we want to get x by itself. I'll add 8 to both sides. We get 8 is equal to 3 times x. To get x by itself, we'll divide both sides by 3. And I'll use the commutative property just to switch it around to say x is equal to. You can leave it as 8/3, or you can write it as 2 2/3. I wouldn't put it in decimal form because it is a repeating decimal. So we'll just say x is equal to 2 2/3. So this indicates to us, again, this means that there's an x-intercept located at 2 2/3, comma 0. Okay, in this example, we're going to look at solving a quadratic, which is factorable. So we want to find the values for which g of x is equal to 0, given g of x equals 2x squared minus 7x plus 6. First thing we're going to do, we're going to substitute in, instead of g of x, we're going to place it with 0. So we would say 0 equals 2x squared minus 7x plus 6. And since it's already set equal to 0, we want to see if it's factorable, although up here I do say it is, so hypothetically it should be. In this case, the target product, remember target product is a times c. A is 2 and c is 6, so 2 times 6 is 12. And our target sum is the coefficient of the middle term, which is -7. So we're looking for two numbers that multiply to 12 and add up to -7. I think our winning combination will be -3 and -4. So what we do is we replace -7, right? Because -7 is also -3 and -4. We're going to replace -7x with -3x and -4x. So it's going to be 2x squared minus 3x minus 4x plus 6 is equal to 0. Now we can factor by grouping because we have 4 terms. So I'm going to group the first 2 terms. Make sure I change that to plus negative there so I don't lose a negative or do anything weird with that. And now in each grouping, we're going to look for the greatest common factor, the GCF. The GCF of 2x squared and 3x is x. That would leave us with 2x minus 3. Over here, not only are we going to factor out the GCF of 2, we're also going to factor out a negative because we don't want the first term here to have a negative. So we're going to factor out a -2, meaning we're going to divide both terms by -2. That will give us 2x. Positive divided by negative is -3. Now we're down to two terms. These two terms have a greatest common factor. We can pull out that greatest common factor, 2x minus 3, and write what's left from each term. The first term has an x left over, the second term has a minus 2 left over, equals 0. Now it looks like we're going to have two zeros. One is when 2x minus 3 is equal to 0. The other is when x minus 2 is equal to 0. If 2x minus 3 equals 0, then 2x is equal to 3, and x is equal to 3 halves or 1 1/2, whichever way you want to write it. I don't know why I put a comma there. And here we're going to add 2. We're going to get x is equal to 2. So this indicates we have two zeros or two x-intercepts. We can say x is equal to 1 1/2 or x is equal to 2. In our next example, we're going to look at a quadratic that's not factorable. So we're going to find all values for h of x equals 0, given h of x is equal to 3x squared plus 6x minus 7. So first we're going to substitute in, we're going to say 0 equals 3x squared plus 6x minus 7. And we want to double check that it really isn't factorable, because if it is, it's a lot easier. The target product here is 3 times negative 7, which is negative 21. And the target sum is positive 6. And the only combinations that multiply to negative 21 would be negative 21 and 1, and negative 7 and 3, or you can switch those negatives around, but either way, this isn't going to happen. So now you have a choice. You can either do completing the square, or you can do the quadratic formula. I can show both, because why not? So if we start with the quadratic formula, remember the quadratic formula is x is equal to, hold on, let me just finish writing this. Okay, there we go. Quadratic formula, x is equal to inverse of b plus or minus the square root of b squared minus 4ac all over 2a. In this example, a is 3, b is 6, and c is negative 7. So when we plug in, we get x is equal to, the opposite of 6 is negative 6, plus or minus the square root of 6 squared minus 4 times 3 times negative 7, all divided by 2 times 3. Cleaning this up under the radical, which is also referred to as the discriminant, 6 squared is 36. Minus and minus for the second product, or for the second term that is, would become a positive, so this will become a plus. So we do have two solutions here. 4 times 3 is 12, and 12 times 7 is 84. And multiplying through the bottom, we get 6. I know it's tempting. We see the negative 6 and the positive 6, and it's like, ooh, we can simplify, but wait, because you can't just simplify those two. We have to see if the third one also is simplifiable. This was 84. I don't know what happened to it, but 84 plus 36 is 120. We can simplify 120, the square root of 120. The biggest perfect square that goes into it is, well, 4. That would be 2 times the square root of 30. And now we can simplify all three terms by a factor of 2. We cannot just simplify the two 6's. It has to be all three terms. If you want to split this up into two separate terms, go for it. I think if we do completing the square, you'll see the two separate terms also. So this is going to give us negative 3 plus or minus the square root of 30 divided by 3. So there's two solutions there. I'm going to put them up here. The two zeros, or the two x-intercepts, are negative 3 minus the square root of 30 divided by 3, and minus 3 plus the square root of 30 divided by 3. If we were to do completing the square, so completing the square, we do need the x squared term to equal, to have a coefficient of 1. So what we'll do is we'll divide everything by 3. So dividing 0 by 3 will give us 0. Then we divide by 3, we get x squared. Here we divide by 3, we get 2x. 7 divided by 3 is 7/3. I'm going to keep it an improper fraction. Now to complete this, so this is 2/3 of a perfect square. We can take that b term, the 2, and we divide it in half, which would be 1, and then square that. And I'm going to add 1. I'm going to keep that minus 7/3. Now, I just added 1 to one side of the equation. You can't just add 1 willy-nilly. I have to also then undo that plus 1. And the way I can undo a plus 1 is to take away 1, right? So now I've really done nothing to this because I added 1, but then I took that 1 back away. Now we're ready to factor. we're going to get x plus 1 quantity squared minus, 1 is equivalent to 3/3, so that would become 10/3. Now, we're running out of space. Now we want to get the squared term by itself. So I'm going to come over here, just due to lack of room. And we're going to add 10/3 to both sides. So we're going to have 10/3 is equal to x plus 1 quantity squared. Now we're going to take the square root of both sides, but when you take the square root of that numerical side, you have to add that plus or minus. So we have plus or minus the square root of 10 over 3 is equal to x plus 1. Now we want to get x by itself, so we're going to subtract 1 from both sides. There's -1 plus or minus the square root of 10/3 is equal to x. Really, we're not supposed to have a denominator or a fraction in the radical. So to rationalize the denominator, first we would think of this as root 10 over root 3, and then we would multiply both the root 10 and the root 3 by root 3, giving us -1 plus or minus the square root of 30 over 3, which does match what we have here, right? Because if I split up and rewrote this as -3 over 3 minus root 30 over 3, this simplifies to -1. So it ends up, either way, it works. Okay, we survived the quadratic not factorable. Let's look at an absolute value function. So this time we're given r of n equals 0, and the function is r of n is equal to the absolute value of 2n minus 7 plus 3. So first we're going to substitute 0 for r of n, then we get the absolute value of 2n minus 7 plus 3. We want to consider the cases, but in order to do that we need to isolate the absolute value, so we're going to subtract 3 from both sides, giving me -3 is equal to the absolute value of 2n minus 7. When I subtract 3 over here, it's going to cancel. So now we want to think about this. So we have an absolute value equal to something negative. Absolute value is non-negative. So we have a contradiction here. This indicates to us that there are no zeros. There are no zeros to this function. We have to be super careful about that. Okay, in this example, we're going to look at finding the zeros of a square root function. So first, just like with everything else, we're going to replace f of x with 0. And then we're going to say 0 is equal to x minus 3 plus 4. We want to get the square root by itself, so we're going to subtract 4 from both sides. Then we get -4 is equal to x minus 3. Now that the radical is by itself, what we do is we square the entire left-hand side and the entire right-hand side. -4 quantity squared is 16. The square root and the square kind of cancel. And now we can solve for x by adding 3 to both sides. Now, with radicals, we do have to be careful because we did do something that technically isn't totally legit, which is squaring both sides. We need to make sure that 19 really does produce a 0. So we must, this is the first time that we must check our work. So we're going to plug in, we're going to make sure that 0 really does equal the square root of 19 minus 3 plus 4. And when we do that, we get the square root of 16 plus 4. This is 4 plus 4, which it turns out does not equal 0. So this did not work, indicating again a contradiction, no zeros. So this one also, just like that absolute value, had no zeros. Hopefully you found these helpful. Thank you for stopping by.